Calculate turning points/pivot points in trajectory, path. I'm trying to come up with an algorithm that will determine turning points in a trajectory of x/y coordinates. The following figures illustrates what I mean. Green indicates the starting point and red the final point of the trajectory. The entire trajectory consists of 1,500 points. In the following figure, I added by hand the possible, global, turning points that an algorithm could return. Obviously, the true turning point is always debatable and will depend on the angle that one specifies that has to lie between points. Furthermore, a turning point can be defined on a global scale, what I tried to do with the black circles, but could also be defined on a high-resolution local scale. I'm interested in the global, overall, direction changes, but I'd love to see a discussion on the different approaches that one would use to tease apart global versus local solutions. What I've tried so far. Calculate distance between subsequent points. Calculate angle between subsequent points. Look how distance/angle changes between subsequent points. Unfortunately, this doesn't give me any robust results. I probably have to calculate the curvature along multiple points, but that's just an idea. I'd really appreciate any algorithms/ideas that might help me here. The code can be in any programming language, MATLAB or Python are preferred. Edit: here's the raw data, in case somebody wants to play with it. Mat file. Text file, x coordinate first, y coordinate in second line.
The approach you took sounds promising, but your data is heavily oversampled. You could filter the x and y coordinates first, for example with a wide Gaussian, and then downsample. In MATLAB, you could use x equals conv x norm minus 10 column 10 0 5, and then x equals x1 column 5 column end. You will have to tweak those numbers depending on the intrinsic persistence of the objects you are tracking and the average distance between points. Then, you will be able to detect changes in direction very reliably, using the same approach you tried before, based on the scalar product, I imagine.
A very interesting question. Here is my solution, that allows for variable resolution. Although, fine-tuning it may not be simple, as it's mostly intended to narrow down. Every k points, calculate the convex hull and store it as a set. Go through the at most k points and remove any points that are not in the convex hull, in such a way that the points don't lose their original order. The purpose here is that the convex hull will act as a filter, removing all of unimportant points, leaving only the extreme points. Of course, if the k value is too high, you'll end up with something too close to the actual convex hull, instead of what you actually want. This should start with a small k, at least 4, then increase it until you get what you seek. You should also probably only include the middle point for every 3 points where the angle is below a certain amount, d. This would ensure that all of the turns are at least d degrees, not implemented in code below. However, this should probably be done incrementally to avoid loss of information, same as increasing the k value. Another possible improvement would be to actually rerun with points that were removed, and then only remove points that were not in both convex hulls, though this requires a higher minimum k value of at least 8. The following code seems to work fairly well, but could still use improvements for efficiency and noise removal. It's also rather inelegant in determining when it should stop, thus the code really only works, as it stands, from around k equals 4 to k equals 14. Here is a screenshot of the above code with k equals 14. The 61 red dots are the ones that remain after the filter.
Another idea is to examine the left and the right surroundings at every point. This may be done by creating a linear regression of endpoints before and after each point. If the intersecting angle between the points is below some threshold, then you have a corner. This may be done efficiently by keeping a queue of the points currently in the linear regression and replacing old points with new points, similar to a running average. You finally have to merge adjacent corners to a single corner, e.g. choosing the point with the strongest corner property.
I will be giving numpy sippy code below, as I have almost no MATLAB experience. If your curve is smooth enough, you could identify your turning points as those of highest curvature. Taking the point index number as the curve parameter, and a central differences scheme, you can compute the curvature with the following code. You will probably want to smooth your curve out first, then calculate the curvature, then identify the highest curvature points. The following function does just that. Some explaining is in order. Turning underscore points is the number of points you want to identify. Smoothing underscore radius is the radius of a smoothing convolution to be applied to your data before computing the curvature. Cluster underscore radius is the distance from a point of high curvature selected as a turning point where no other point should be considered as a candidate. You may have to play around with the parameters a little, but I got something like this. Probably not good enough for a fully automated detection, but it's pretty close to what you wanted.
If you want to support the channel, please consider liking and subscribing.